finally time to start on the problems of section 3. It's been a long and cold winter. Well, the winter has not been cold, I just had a cold. And a lot to do. But let's get started on the problems. First, we define the map T like this, tilde. This lies in Gamma order 4, so it's well defined how to find the autonomy factor. I'll just write the alpha phi of z gamma and we know the inverse. It's 1 divided by phi of the inverse of alpha of z. First, we must show that it does not depend on the phi that's chosen, and we need not compute this explicitly. We can just say that if we put a t on here and then the same t here and then multiply them, then the t's will finally cancel. So that's easy. Next, it's a group homomorphism. And this is alpha 2 to minus first, and then we insert an alpha here, gamma 1 minus first, Now what we need to show that it's equal to is t of gamma 1, t of that's a little weird. So we need to show that it's equal to alpha gamma 1 minus first, alpha minus first, I would just call this psi. mind, that's weird. And we also need to show that T of the identity matrix, this unity, that should be easy. This, of course, gives the identity matrix, and yeah, that's easy. It's trivial. I just don't write the projection to T here, so never mind that. But I don't know how to do this really. Of course, this lies in gamma naught of 4, and so does this. So that means that the A factor actually here comes from each of them separately. Still wonder how come we can split it up here and just take those two and then the other, those two first. They are actually written up so that this is, no, I'll just do it in color. This, and then alpha phi gamma 1, alpha phi inverse, and then we have alpha phi gamma 2, alpha phi the inverse, and the blue ones give T of gamma 1, which is a number we can just take out. So we get directly, and then we can take T out in the front because it's the unity matrix and just a number. And then what's left, that's just, it's called T, not tau, isn't it? Yeah. And then we haven't shown that the t of the reciprocal is the is 1 divided by t of gamma. So to do that, we need to show that tau of, oh, I had already did that. Yeah. So that was the first part. I need to tell you that when studying this section, I suffered from a terrible misunderstanding. And when I read this, which also is in the section, by the way, but I didn't notice it at the time, there was a cognitive dissonance, because in one sense it seemed obvious, and then, well, the point is that you see in chapter 3 we defined gamma mark double mark to be gamma mark intersection by alpha to minus first gamma mark alpha. And I thought that extending this would be the same as extending each of these. But this is exactly the point that it need not be, because if an element here will have the automorphy factor dA of gamma point z, but this may come out to gamma point something else. And in that case, the matrix gamma is not added to this set at all. And then it becomes obvious that it is added to the set to this set exactly when these two are the same, and that means that it is in the kernel. And now I need to make an example of these two not being the same, and I have seen the next exercise, I read the next exercise, that we can find an example where they give opposite sign. So I will just do that example, and then I will go on with this problem. The example in question oops, it should be 4, 6. And it comes from, so we just need to, of course this has the automorphy factor 1 times 4z plus 5, or the square root of it. So let's compute this. This is 3 to 1/4. So this is 3 to the reciprocal. And epsilon of 5 is unity, so it's just square root of 12z plus 5. And we must operate on this, on z with this matrix, and then multiply by the 4th root of 3, and multiplying together 5, 6, 4, and 5. And then we must operate on this guy, the set of, but that's just a constant, so that just gives the same, and then multiply by this. And this is in stark contrast to the result we should get by problem 2, where it should be d on n, which is 5 on 3, which equals minus 1 on 3, which is minus 1. So I get that this matrix lies in the kernel, and by problem 2 it shouldn't. So I need to find my mistake. Well, I just found it. I forgot the autonomy factor epsilon d I did get, but c on d I didn't. So this we need to add 12 on 5. 12 on 5. 2 is not a square, so that's minus 1. But 4 on 5 here, that's plus 1. Shouldn't it be 3 on 5 but on the other way? I think it should be n on d. In this case, they agree. So finally, I'm ready to get started on understanding it in depth. That was very terrible. I spent quite a while working on false assumptions. Of course, I did get a lot of examples under my belt, which is always a good idea. I'm back again, having solved problem 2, by the way. It's February the 21st of 2025. We need to generalize proposition 42 of chapter 3, because it's quite formal that if we do the same, it should hold. So we have a group gamma mark tilde, a subgroup of gamma naught tilde of level 4, and then we construct gamma double mark tilde, the intersection psi n to minus first, gamma mark tilde psi n. Now if we project to the matrices, then this of course projects to gamma 1. And then we have gamma double mark. And on this we have t, which maps to plus minus 1. And this is the kernel of t. And that means that there will often be elements of this one which does not lie here. And the way it can happen is that coming from this and this, the same matrix will result in different values of, or opposite values of the automorphy factor. And that means that this guy will have index 2 compared to this. So the index is 2. And now everything becomes clear, and it's actually they already went through it in the book. So I'll just do an example where gamma mark is gamma 1 of level 4, and n is equal to 3. We already have written gamma double mark here as a disjunct sum of right side classes, and then the last one I should have it here. There are many possibilities. I just chose -3, -3, 4, 2. We must find one matrix that is not in the kernel, that maps to -1, and that should be easy. I have it right here, I think. So that means that gamma doesn't lie in the kernel. So we have index 2, and that means we can write up all the right-hand side classes. First, the ones we have. Four on -3, that's 1. And then comes the one where we just add this matrix. So the index of this is 8 in this group. Now we know that operating from the right with gamma permutes the right-hand side, the right side classes, and since they all have the opposite sign, did we check that? Well, it's actually in the book, so I don't need to do that detail. And that means that when n is 3, it vanishes, and it easily generalizes as long as n fails to be a perfect square. Then this will have an index in, or this will have an index in that, and then we'll have the sign changing. why this guy will vanish when we generalize to half-integer modular forms, because we have to exclude some when computing this guy, and when t is not trivial on these matrices, then it will vanish, and that happens exactly when n is a perfect square. So that finishes my work on problem 1, and now I feel I've cleared up my misunderstanding.